most of the, no, not more, all the experiment data which I'm going to show you is essentially taken from the Professor Young group at South Korea in APS. So let me start with that. So indium silicon is an extremely popular model system for studying one-dimensional physics. It came up studied long way back, like in 2005 or even before in 1997, something like that. So it comes with a temperature-induced reversible phase transition where we have 4x1 phase and an insulator phase, which is called the 8x2. It's come with the 8x2 lattice translational function. So as this is a first order phase transition, so we may able to get some interesting exotic overlap phases. So this is the current topic of my discussion, and what's happening at the interfaces. So well studied by experimentalists and theoreticians, and it's well understood as a first order phase transition system, then it makes sense what's happening at the interfaces, because then it's exotic in nature. So I will go a little bit deep into that. For example, this is a very busy slide, look like, but you can see there are two regions, dark and blue one, bounded by blue. In blue bounded region, you might be noticing some very shiny features. This corresponds to protrusions of anode periodicity of the 4x1 metallic phase. And in the red region, this corresponds to the protrusions, oval-shaped protrusions of 2 anode periodicity of the 8x2 CDW phase. On the other hand, you might be able to notice there are some bright features essentially coming from the atoms or clusters of atoms. Then it's natural. You will get these dark features with vacancy or the clusters of vacancy. So the clusters of vacancy and atom when combined together may end up with very irregular phases. But I will discuss something that is happening, like for example at the edge of this or something like this here. So we have well-defined phases, and also we have some irregular phases. But let's choose for the well-defined phases, which come in two flavors. This is the intrinsic junctions, and the second one is the defect-induced abrupt phase transition type of junctions. Then, although these phases we can notice not only along the wire, but also in perpendicular to the wire, long and straight along the wire, abrupt and irregular perpendicular to the wire. So this kind of strong anisotropic nature of the system suggests it's a pretty good candidate for the one-dimensional physics. So let me begin with that. For example, I want to separate these two scenarios here, and if you go to this is the 8x2 oval-shaped protrusions experienced in both kind of structures. And next, this is the 4x1 phase which comes with the anode periodicity in both structures. And now if you follow across this arrow, with this broken line, you will see that it's changing quite gradually from 8x2 to 4x1 shape, depending on the brightness of the feature, because the 4x1 is the only phase which has the metal electron. So they are bright and shiny. But here, if you notice, this is okay, like this one, and then here happens something, and we get something like very abrupt phase transition, and it's essentially the 4x1. And it's obvious in the STS spectra of the experimentalists, where you can see this kind of gradual transition. It's something like the density of state because I'm a theoretician. So it's something like density of state is decreasing like quite gradually, and here it's very abrupt. So we want to model atomistically what is happening here and what is the underlying physics of both of these kind of junctions. So I will go like that, how the defect is influencing this kind of phase separation and how we can model this phenomenon. So we can take as ingredient what's the mechanism behind 4x1 to 8x2 transition, and from there we can explain these kind of junctions. So before going to the atomistic model, let me explain a little bit about this phase transition. So this phase transition is actually comes with the triple band piles triple well junctions. Here, the ultra fast dynamics people, they shine some, how to say, the femtosecond laser pulse and melt this CDW junction will go up here. But immediate coming back is hindered by this much energy barrier. And then it stays there for a quite long time as a supercooled liquid state. But ultimately it's triggered by pre-existing adsorption. But this kind of phase, which is a melted CDW phase, and phase staying there for quite long time, it's a good candidate for the first order phase transition. But nevertheless, it comes with the 3 bands. So the shear mode will lift one band above the Fermi surface and leave the vast ground for the remaining 2 intermetallic surface bands, which are actually the rotary modes, and open the gap band. In the same time, they are flipping the bands. So this feature is essentially due to the topological nature of this material. With this in hand, I will use them as building blocks for my atomistic modeling, and it's a simple linear algebra. We can do like this for 4x1, some coefficient time the shear mode, and some coefficient time the trinal modes, and so on. So with this in hand, then I can go like that way. For example, if I start with the gradual structure and run a standard ab initio calculation, we always end up with the abrupt structure, even without a datum. And the reason is hidden in the triple well potential, because both phases can coexist in a very minute vicinity, so it means that temperature drift is necessary. Then we run an ab initio calculation, for example, fixing some part here which correspond to the 8x2 phase and some part here which correspond to 4x1 phase, and take a long trajectory and taking the statistical average of 50 picosecond trajectory. Of course, it's quite long compared when you see it's a 2 substrate layer or 3 substrate layer and atom system size going beyond 700 atoms. Anyway, but you can notice that it's a quite nice match. This is the experimental image, and here you can see very gradual change, and then finally become 4x1. Counterintuitively, we can do the reverse analysis, then what's happening on the level of shear and rotary modes, and we can see that the shear and rotary modes are decaying quite linearly, and that's the way how we can model this configurational coordinates of this system when we expand this empty trajectory into phonon modes. Now the next question is how the defect is making influence in this structure. So that's come like this way. When we induce defect, it comes essentially with the phase flip defect, and these kind of 2 defects are well studied for this system. One is called phase flip defect, another called phase slip defect. But the nice thing about the phase flip defect is that this area is then sterically constrained, which means that it can no thermal fluctuation can visit them. And then it's simple, because you can say that here these are the 3 modes, then they are just changing their sign from +1 to -1, and it's very rigid, and it's there. Even if you impose some temperature effects, this region will not go beyond that. And the position of defect is there. Here is this bright region is coming because of this one, and here is the 4x1 phase, well matched with the experiment, and here is the 8x2 phase, which is essentially this one. So with these 2 features in hand, now I can also go. Defect can not only trap these metal insulator type junctions, it can also trap something like CDW junctions, which is actually the topic of my PhD. I'm working for that, but it's coming upward. But I'm already at the end of my talk. For example, we study 2 systems which are intrinsic, and in an atom we have gradual phase transition, we call it intrinsic junction, or we have abrupt phase transition, which is immune to thermal fluctuation. And the next thing is that we can use these addendum to trap the CDW type junctions. We can use the 3 phonon modes, and it ends up like 8 structures, and 4 of them are topologically allowed and 4 are topologically band structure. Then with the 4 allowed structure, we can build 12 phase boundaries, and these phase boundaries are nothing else but the solitons. These 12 phase boundaries then come with 3 different flavors. That's called the right chiral one, left chiral, and the anti-chiral solitons. Once we can build that, then we can go for studying the electronic properties, or even we can study the soliton interaction, soliton defect interactions. It's quite interesting interactions because, for example, the anti-chiral soliton can move the defect, and others can shift. It's something like this. It follows the abelian group algebra. For example, you have a left chiral soliton, and here is the right chiral soliton is coming, then you will end up with a ground state, and something like ground state with the right chiral and end up with the left chiral soliton. So we want to use this abelian group algebra for the quantum computation at the end. With this, I'm already end, and these are my financial supporters.
Thank you very much. Questions of this talk? Do your solid atoms have fractional charges? Or
Yeah, fractions are, they come with, for example, one comes with a positive charge, one comes with a negative charge, and the other is neutral. So we want to use